Hi everyone, hope you're doing well. Welcome to this week's Friday presentations. Today I'm going to be giving a talk on a really interesting paper called Towards Effective, Efficient, and Unsupervised Social Event Detection in Hyperbolic Space. My name is Griffin Higgins, and my supervisors for this directed studies project are Prof. Ali Gurbani and Dr. Xishan Zhang. A little bit about me. I'm a PhD student here in the Faculty of Computer Science at UMB. I'm also a cybersecurity software developer here at CIC, and I love nerdy things. Some of you may know that I just took a quick trip to Washington, D.C. While I was there, I was at the International Spy Museum, and they actually showed off one of the 007 cars in the lobby that they had, so that was very cool to see. I have many other interesting nerdy things. I'm starting to run out, so I'll be showing you those over the next coming weeks or years maybe. So with that, we'll kind of skip the introduction. This is going to be a standard presentation. But we will go over some motivation. So just like in other weeks, this isn't anything special. We're focusing on social event detection. So we might think about events that occur. They're often important and they have some kind of location and temporal nature to them. They often are propagated through social media by people that observe these events. And we can understand that that's really important. And most importantly, on social media, we can extract lots of documents and maybe perhaps gain insights into how these events might be occurring in real time in the world. So the whole framework kind of looks like this, where we might have this kind of social media setting, we might have documents, and we might have events that we can derive from the documents that we're going to try and identify or categorize and track in various ways. So that's not new, but today we're going to be shifting from kind of a supervised setting to an unsupervised setting. Critically, in a supervised setting, we have the labels. We know the ones and the twos for the cats and the dogs. But in this unsupervised setting, we don't necessarily have the labels to train our kind of machine learning algorithms to recognize the cats and the dogs. Instead, what we're going to do is we're going to try and cluster them in high-dimensional space. So here, even once we have a cluster, we might not know exactly that it is representative of the cats or the dogs, but we just know that we have clustered those things together. And maybe later on, we can go and figure out what actually is in the cluster. But that's what we're more interested in today, is this unsupervised nature. This, of course, is important in social media, where we have lots of streaming data. We're interested in millions of documents that are currently or consecutively flooding in, and we're interested in extracting and identifying events that might be changing. So again, the labels might be different. It might not be that the labels that we've had in the past are representative for predicting the labels in the future. We might say at a high level this would be true if we're talking about politics or things like that, but again, we're focusing specifically on events. So maybe like natural disasters, those might be different in the future than they are in the past, so we want to identify those in an unsupervised way. So a lot of this is going to be looking at the methodology. I picked this paper mainly just because it looked very challenging to understand, and also because it obtains very good results in this unsupervised setting that I'm interested in. So the method they propose is called Hyperbolic SED, or social event detection, and we're going to kind of break it down a little bit today, just like in past weeks. So at the very start, we're going to start off with Twitter. We're going to have Twitter, and we're going to extract documents in the form of messages, i.e. the text in the tweets that people post. And we're going to say that they're going to constitute M1, M2, up to Mn. After this, we're going to perform named entity recognition on these documents. And this is just a fancy way of saying, like, we're going to try and identify like the people in the tweets, or the locations in the tweets, or whatever we would otherwise define to be an entity. We can also take a look at the hashtags within each kind of tweet. We can also understand that there's different users that might post tweets. So that's very interesting for us. And we can relate the messages to these entities, or to these hashtags, or to these users. But most importantly, we can actually start to relate the messages themselves together through their relationships to their entities, or their hashtags, or their users in the following graph. So that's very interesting, and this is going to form what we're going to know as the entity graph. And we're going to save it in the bottom left-hand corner, just so it doesn't go out of our mind as we start to traverse through the rest of this architecture that I'm going to show off today. Afterwards, we're going to go back to the very start. So we're going to wipe the slate clean. We're going to start back with the messages, and we're going to compute the message embedding for each message using a pre-trained language model. So in this case, we might think about things like sentence transformers that we've demonstrated in the past that will take this message and put it in very high dimensional space, where similar messages will be in similar locations. We're going to compute this on the fully connected graph between all of the messages, and then we're going to weight the fully connected graph on the edges by how similar two messages may be. Afterwards, we're going to start to construct different types of graphs using what's known as structural entropy information, I believe, on the graph, and that takes the following form. And here what we're interested in doing is we're wanting to create a graph that's not too sparse but not too dense, but that's representative of the relations between the messages with respect to their similarity. So we're kind of building this semantic graph. Afterwards, we might take the best one. So we're going to minimize this kind of this cost function, and we're going to say this is going to be the most representative semantic graph for all of these messages. Afterwards, we're going to take this graph and we're going to put it in the top left-hand corner, and then we're going to take the graph that we had in our bottom left-hand corner that we can recall from just now, and we're going to fuse them together. So all the edges that would have been in one graph will be edges in another graph. So that will look like this, and this will constitute our final message graph. So here, just again, if we look at this blue node and this blue node, it doesn't have an edge in this top graph, but if we look at this blue node and this blue node, it has an edge in this graph. Therefore, if we kind of just sum them up, it will be all the edges between all of the nodes because the nodes are the same in both graphs. All right, we're also going to save this. So we're going to do this same process. We're going to put it to the bottom left-hand side of our screen just so we can remember that we have it. And then, of course, we're going to go back to the start of our graph again. And now we're going to construct what are called anchor graphs. So we're going to take all of the similar messages in parts of the graph, and we're going to basically group them in little groups. So here we can see all of these three green nodes will kind of form this little green blob, if you will. And then some of the other ones might not be perfect. So we might have like these two blue ones here will form like one blue blob, and then one might just be by itself. We actually have to specify how many of these anchors that we're gonna consider in our graph, so that's important for later. But yeah, we're gonna have this graph. And we use this in order to reduce the size of the graph itself, because we think about social media, we might have millions and millions and millions of messages. So if we're going to start computing anything on very large graphs, our lives often become very difficult. So we need a way to actually reduce the size of them. After we do this, we're going to take that anchor graph where we're kind of forming similar messages in blobs, and we're going to bring up the message graph that we had before, and we're going to start connecting the blobs together by the edges that would otherwise exist in the graph below them. So this will form our final graph, and it's going to be called the semantic-based anchor message graph. So of course, this is going to take into account the entities and the users and the hashtags, as well as the semantic similarity between those graphs. So after this, we're going to take our semantic-based anchor message graph. Sorry, it's a bit of a mouthful, it's hard to remember. And we're going to place this onto hyperbolic space. We might think, why would we do this? In past weeks, we can recall that this hyperbolic space is nice because it gives us a way to represent hierarchical relationships that exist between messages and in text rather efficiently and effectively. So that's very good and has proven it works well. So after we do this and we take this graph and we place it onto the space, we're going to use something that's called a hyperbolic graph autoencoder, and we're going to condense the representation for this graph in hyperbolic space into a very low dimension, and then we're going to bring it back out and decode it into a higher dimension. We have some formulas for this. We can go over them later if you're interested in it. But the key part of this is that at the end of the day, we're going to have this output graph. And this output graph is what we're going to use to measure how good it represents the input graph that we started with. And we can formalize this numerically with the following. So we're going to take the loss of this hyperbolic graph autoencoder, and we're going to say that this is going to be how well the input reconstructs the output. And after a while, if we can do this well, we can say that whatever that little smaller dimension is in the middle will be actually representative for us to use. So this is great. This is the top part of the second half of the methodology. But really, again, we want this lower dimensional space in the middle. That's our whole aim of doing this. Afterwards, we can take that embedding as well as the previous graph, and we can take a look at all of the leaf nodes of this graph. And remember that these are kind of the anchor graphs, so each of those nodes actually constitutes a lot of nodes within them that are similarly representative of whatever that is. Afterwards, we can start to perform this operation where we start to build up this tree bottom up, and here we can see that it's kind of hard to explain, but at the start here, we're going to basically take the mean of all of the embeddings of the nodes within them to represent that leaf node. And then what we're going to do is we're going to optimize how we construct the edges to minimize the entropy at each level of this tree going up. You might say, why would we do this? The whole point of doing this is so that we can learn to cluster all of these anchor graphs that represent the millions of little nodes that they represent well. So that's why we would do that. So we're at the end of the experimental, or at the end of the methodology. I know that's quite complicated. It wasn't too easy to understand myself, but I think that's not too bad. We can also take a look at the experimental setup. So here, the authors consider the English Twitter dataset and as well as the French Twitter dataset. This is somewhat confusing. In the literature, this is often referred to lots of different names, so they call it the Events 2012 or the Twitter 2012, but they're all talking about the same thing. And they also consider two settings. So one is this offline setting where they just consider the whole data set as one coherent block. But then they also consider this online setting that would be more representative of real life, where we might have some block of messages that come in at some time step t, and then some new block of messages that come in at time t+1, right? So that would be more representative of the real world as it relates to this being streaming data, so that we're clustering these events through time. So that's a little bit about the offline and the online, and they split the training and validation and the test sets into 7, 1, and 2 ratios respectively for the offline set. For the baselines, they use several non-graph-based methods. So they use BERT, they use SBERT, and they use event X. And then for the graph-based methods, they use KPGNN, QSGNN, and HIS event. Mainly, the authors are focused on this HIS event. It's the most closely state-of-the-art method in an unsupervised setting to what they're doing, so that's why they focus on it quite a lot. And for metrics, they use normalized mutual information, adjusted mutual information, and the adjusted RAND index. These aren't very common, but again, we can remember that this isn't a supervised setting. It's not like all the cats are going to be 1 and all the dogs are going to be 2. Where we're just going to see does the 1 equal to 1, does the 2 equal to 2? This is an unsupervised setting. So even if we have labels, the labels are going to be representative of clusters or groups. So even if we predict a different number, as long as the same group of numbers in the prediction matches the same group of numbers in the cluster label, it's okay if they're different, but just as long as those samples are the same, that's what we're interested in, because it helps us define the quality of our unsupervised clustering. So that's why these are used. And the other metrics basically consider the effects of random choice as well as the size of varying clusters themselves. So that's why they're used. In terms of the evaluation, the long story short is that HyperSED gets a 2x performance boost on one of the hardest metrics, the adjusted RAND index, over some of the best baselines. It's also interesting to see when we look at the metrics, if we look at the normal mutual information, normalized mutual information, and the adjusted mutual information, that the non-graph based methods do quite well in the second, in the runner-up kind of category. But then once we flip to the adjusted RAND index, then all the graph-based methods start to do better. So maybe the adjusted RAND index is a better metric for actually evaluating all of this stuff. So yeah, that's wonderful to see that it actually gets 2x performance. I'm doing a little bit of work on this right now, and I can tell you that that's pretty hard just to do. I'm happy if I can get just a little bit of improvement with stuff sometimes. So that's great to see. I'm not going to show you the offline or the online settings because we would be looking at tables for forever, and they would be huge. But just to sum it up, when we look at the English Twitter set, the method proposed by the authors, it wins or it gets the best in 71% of those message blocks, i.e. the times where we're trying to predict new events through time. So that's really great, and it gets the runner-up in 28% of those cases. In the French Twitter dataset, it wins 68% of the time, and it gets the runner-up 25% of the time. So I would say that's pretty good. The authors also consider different parameter settings. So they consider the partitioning tree height that they vary, as well as the number of the anchors. That's something we talked about, that was epsilon. So yeah, that's interesting as well in the offline and the online setting. And then lastly, and most importantly, the authors in the title, they talk about efficiency and effectiveness. Here, the efficiency kind of standpoint, when we're looking at how long does it take to actually construct these graphs is a big concern whenever we're looking at graph learning based applications. So here we can see that there's a speed up of roughly 27 times if we're just considering the offline setting. This will vary in the online setting because some of the message blocks have different numbers of messages and events in them, so that's not too bad. But in every case, there is a speed up, so that's also wonderful to see. Just as a developer, it means I can look at this and say to my boss, this is going to be 30 times faster, this is going to be X many times faster. In terms of the ablation, the authors look at basically the ablating the different types of the graphs that we constructed earlier. So when we were thinking about the entities or the semantic relationships between the graphs, or when we combine them in different ways, it turns out that their method gets the highest, sometimes without the hyperbolic graph autoencoder. In the English Twitter offline setting, they get the same performance. So that's interesting. But in the online setting, we can see that it also makes an impact. So that would be good if we're going to consider this for real world applications, that we want the full architecture that the authors propose. So in conclusion, the authors propose a social event detection framework called HyperSED. The emphasis is placed on efficient unsupervised setting, and they get great performance with 2x on whatever the state of the art is on a very challenging metric, so that's great to see. Moving into some of my critical review, as great as the work is, I think it's very interesting and challenging to understand. But if HyperSED is so efficient, then why can't it be run on more data sets? In this experiment, they only run it on 2 data sets, but there's many more. So and different ones are used in different papers for comparisons, so that's kind of a little bit questionable. Also, why is the absolute rather than ratio of the performance not mentioned? So like if I have an algorithm, it takes 1 month to run, versus like if I have another algorithm and it takes 27 months to run, like yeah, that's still 27x increase, but it still means you have to run round rhythm for a month, right? You might not be able to do that. So maybe just report like what's the absolute time, maybe it's 1,000 seconds or something, that's enough. Also, some data sets do not make the users known. How would this be handled in some settings? Some data sets don't include that. I would also ask what specific entities are extracted from the messages and how is this done? Are you extracting locations? Are you extracting people? Or like what are you doing? And then why is the ablation of users and various entities not performed? Like what happens if you have all these entities and maybe you exclude all the users or you exclude all the locations? Like how does that change? That's a bit of a nit. It's a little fine grained, but it would be interesting to understand. I would also say like what prevents the inclusions of the data sets in the implementation. I didn't see that there, and they're not too large, so that's interesting. I would also ask where is the baseline models in the implementation? I didn't see it there. And after some digging, they use the all-mini LM L6 V2 pre-trained language model, which is it's like a baseline standard sentence transforming encoder that's used. It'd be nice if this is stated just rather than the work, just so people can quickly go, oh yeah, here's the implementation of this thing. So that would be good. And also I didn't see it actually used in the work, so I'm not sure where that is. Other questions I would say are why are other clustering methods not considered? I think they only use like k-means, but this shouldn't be too expensive considering it's just like the last step. Also, like if we have to specify the number of clusters, sometimes this can be challenging, so why not use methods that don't have this, like dbScan or hierarchical dbScan? And why isn't time considered as part of the node embeddings? That's a very common thing we see in a lot of the works. They just append it on the very end. I know in my own work when I've done this, you see a huge boost. so that's good. And then why aren't state-of-the-art pre-trained language models used? I mean, this all mini LM models very good, but we have much better models now, like these Quen models. I'm sure you could see a very big performance boost just if you swapped those things out. That shouldn't be too hard. And then in terms of my personal review, testing with datasets shouldn't be too hard to do, kind of leading in from the critical review. But I would say, like, if sometimes people would say, oh, well, it's challenging to find these, or it's challenging to implement and get all the data sets and format them in certain ways. This is already done. There's a work that basically standardizes this as a nice Python library, so you don't have to think about managing all these data sets. You can use them in a standardized way, so that shouldn't be too hard to do. I think I already mentioned why use k-means, why not use the others. And then other works compute the t-SNE visualizations. This would be helpful, not as like the absolute truth evidence, but just it's nice to see if it actually makes a meaningful change or not. And I would also say let's use consistent terminology for the data sets. It's tricky if 1 minute someone's calling it the Twitter data set, and it's tricky if another minute someone's calling it the English data set, or let's just try and use consistent terminology. Here's some of my references, and thank you so much for listening, and I'll take any questions if you have any. Thank you so much.